everyone, in this video we are going to discuss theorem number 1.2 and theorem number 1.3. When we are doing the proof of theorem number 1.3, we are going to utilize theorem number 1.2. So understand this theorem properly. Theorem says let P be a prime number. If P divides A square, then P divides A also, where A is a positive integer. First of all, you are going to understand then what is prime number. So, prime number are the numbers which are having only two factors. That is 1 and number itself. Means the numbers which are divisible by only 1 and itself are called prime numbers. For example, you can take 2, 3, 5, 7, 11, 13 and so on. You can see here the 2 is divisible by only 1 and 2. 3 is divisible by only 1 and 3. 5 is divisible by only 1 and 5. Similarly, 7 is divisible by 1 and 7, like this. So they are saying let P be a prime number. So I'm taking, for example, P is equal to, you can take any of the prime number. I'm taking 3 for example. Now if P divides A square, for this I need to assume this A also. So I'm taking A, you can take A 9. Now P divides A square. If P divides A square, so for this I need to find out A square. A square means 9 square means 81 here. They are saying P divides A square means, let's check, A square divided by P. A square is 81 divided by P, we have taken 3. So it is dividing. It is divisible. They are saying if P divides A square, yes, it is dividing. Then P divides A also. Yes, we'll check here. P divides A square, which is 81 divided by 3. Then P will also divide A. So what is A here? P will also divide A. Let's check this also, whether it is dividing or not. What is A? A I have taken 9. And P I have taken 3. Yes. So theorem says if P divides, let P be a prime number, and if P divides A square, then P divides A, where A is a positive integer. So with this example I have explained you, I hope it is clear to you. For better understanding, let's take another number. Take P is equal to, P is a prime number, so earlier I have taken 3, now I'll take P is equal to 5. Now A I am taking a number, any number you can take, 25, let's take 25. Now they are saying if P divides A square, for this I need to find out A square. So 25 square divided by 5, let's check, it is 625 divided by 5. We can check here, 625 divided by 5 is 125. So it is dividing. The theorem says if P divides A square, it divides A also. Let's check whether it is dividing A or not. A is 25 divided by P, which is 5. Yeah. I hope this is clear to you now. Theorem number 1.3 we are going to prove with the help of theorem 1.2. We are going to prove here that root 2 is irrational number. And this we are going to prove by the help of contradiction. So here we are assuming that root 2 is rational. So let us assume root 2 is rational number. So you already know the definition of rational number. The numbers which are written in the form of p by q, where p and q are integers and q should not be equal to 0. So I can write, since root 2 is rational, so I can write it as in the form of p by q. Since root 2 is rational number we are saying, so we can write root 2 is equal to p by q, because rational numbers are the numbers which can be written in the form of p by q. So we are writing here root 2 is equal to p by q, and we are taking that p and q are co-prime. This is very important part, because with the help of this only we are going to prove here that our assumption is wrong. So you are going to write here that p and q are co-prime, and co-prime are the numbers which are having HCF is equal to 1. It means the numbers which are having common factor as 1 only. Now squaring both sides. Squaring both sides. Root 2 square, you can write here only 2. And then p square upon q square. Now take this q square. So it will become 2q square is equal to p square. Here you need to understand that p square is equal to 2 into q square. It means p square is divisible by 2, or you can say that p square is a multiple of 2. So I can write here that p square is divisible by 2. Means p square is divisible by 2. Now we have done that theorem 1.2. It says that if p square is divisible by 2, p is also divisible by 2. I have explained you with the help of an example there. P square is divisible by 2 means p is also divisible by 2. Okay. Now 2q square is equal to p square. It means p square is divisible by 2 means p is also divisible by 2 we have written. Okay. Let's take p is equal to 2k, because p is divisible by 2 or p is a multiple of 2. So I'm assuming that p is equal to 2k. Now put the value of this here. P is equal to 2k. There. It becomes 2k square means it will become 4k square. Now cancel this out. 2k square. Now you can say that q square is equal to 2 into k square means that q square, it means q square is divisible by 2. Again by theorem 1.2, if q square is divisible by 2, q is also divisible by 2. We have understood with the help of an example in theorem 1.2. Now you can see that here I am saying that q is divisible by 2. Earlier I have told you that p is divisible by 2. Means I can say here that P and Q are also having 2 as a common factor. 2 as a common factor. Now, and you can see here that I have written that we have assumed here that P and Q are the coprime. And here I am saying that they are divisible by 2 also. It means P and Q are also having 2 as a common factor, which contradicts our assumption. And therefore, we can say that root 2 is irrational. Hence proved. When you will prove that root 3 is irrational, you are going to use all these steps, and here you are going to assume 3k. That's it. P is equal to 3k. Okay. I hope this is clear to you, everyone. Now we are going to do example number 5. Prove that root 3 is irrational. So again we are assuming that. Let us assume root 3 is rational. If it is rational, then we can write it in the form of P by Q. And we are assuming that P and Q are coprime. Again, I am telling you this line is very important. Coprime means the numbers P and Q are having only one common factor, that is 1. Coprime means the HCF of P and Q is 1. Highest common factor is 1. You can add this line for better understanding. Now we are going to square. So write it here, squaring both sides. While squaring, root 3 square, P by Q whole square. It will become 3 because square and root will cancel out. So P square by Q square. After that, you are going to write down, taking this Q square above. So it will become 3Q square, P square. Since P square is equal to 3 into Q square, means P square is divisible by 3. So by theorem, P is also divisible by 3. Theorem 1.2 says, since P square is divisible by 3, P is also divisible by 3. We have already understood with the help of an example. Now you can write here that P is divisible by 3. So let's assume, let's take P is equal to 3k. Now put this in 1. 3q square is equal to, P is equal to 3k, you are going to put here 3k whole square. It becomes 3q square is equal to 9k square. Cancel it out. So q square is equal to 3k square. Now you can see q square is equal to 3k square means q square is a multiple of 3, means q square is divisible by 3. And by theorem 1.2, I can say that q is also divisible by 3. Now, here you are saying P is divisible by 3. Q is also divisible by 3. Means this assumption is going to be wrong now. We have taken here that P and Q are coprime. It means they are divisible by only 1. The common factor is only 1. But here we are saying the 3 is also the common factor. Here we are saying that 3 is also the common factor. So we are writing here P and Q are having 3 also as a common factor. Which contradicts the fact that P and Q are co-prime. Hence, our assumption is wrong. And then we can say, therefore, root 3 is irrational. That's proved. I hope it is clear to you.